A U-tube manometer is used to measure the pressure difference between 2 points in a vertical section of pipe. The fluid in the pipe is water, density of 1,000 kilograms per cubic meter. The manometer fluid is mercury with a specific gravity of 13.56. What is the pressure difference P1 minus P2 in pascals? So we have a pipe and a manometer here. So this is the pipe, and there's probably fluid flowing in that pipe, but we don't really care about that because what we're going to do is use the manometer, which is this tube, to measure the pressure difference between point 2 and point 1. That's what we've been directly asked to find. So we're going to be focusing on the manometer tube where the fluids are stationary. Fluid might be flowing in the pipe, but the fluid in the manometer tube will be stationary. So we use the diagram we've been given here as our given information, and we'll add to it the fact that this density of the water is 1,000 kilograms per meter cubed, and the specific gravity of the mercury is 13.56. It's really all the numerical information we were given in the problem that wasn't already on the diagram. Notice the displacement of the mercury in the U-tube manometer is given meter. So, what are we asked to find? Let's make our statement of what we're asked to find. And that's very direct here. We're asked to find P1 minus P2. So we can just simply say P1 minus P2. Assumptions. And again, I'm just going to leave space there and come back and put the assumptions in as we make them. Our analysis. So here's where we take a clue from what we've been asked to find, P1 minus P2. So we're asked to find the pressure here minus the pressure there. And we're going to do that by looking at all the pressure changes as we go from this point down through this leg of the manometer, up through this leg of the manometer, and then to point 2. So we're going to start off this problem solution just by saying we want to find P1 minus P2, and we first of all have to recognize that that pressure difference will be calculated by calculating a series of pressure differences through different fluids in the manometer. So let's follow the path in getting from 1 to 2. So we're going to go from here down to here, and the fluid changes there from water to mercury. So I'm going to label that point A. And then we continue to go through our manometer. Here the fluid changes again, so we need to label that point B. And now we're back in water, and we go all the way up to our point 2. So we recognize P1 minus P2 can be written as a series of pressure changes. So it will be, first of all, P1 minus PA plus PA minus PB plus PB minus P2. So this is in water, this is in mercury, and then this is back in water again. And the subscripts on all of these refer to the positions. So P1 minus PA plus PA minus PB plus PB minus P2 gets us all the way between the 2 points we're interested in, 1 and 2. And notice mathematically, P1 minus P2, this is just P1 minus P2 also, because PA and this PA cancel, this PB and this PB cancel. Now the reason we've broken it up into 3 steps like this is because the density is different. So now when we go to calculate these pressure differences, each of these terms will have a different density. So where does this pressure difference come from? Well, it comes always from our basic hydrostatic equation. So this is the starting point for calculating each of these pressure differences that we've recognized that we need. As soon as we write down the basic hydrostatic equation, we need to go to our assumption list and add the fluids that are in a hydrostatic state. Okay, and here we're talking about the fluids in the manometer. The fluids in the main pipe can be moving, so they might not be in a hydrostatic state, but we're not going through the main pipe to calculate this pressure difference. We're going through the manometer. So we've got the assumption written down that always goes with that equation. Now what are we going to do with this? Well, we're going to recognize that in this problem, this acceleration is 0. So we just state here the acceleration is equal to 0. So we're assuming that this entire thing isn't falling or isn't accelerating off to the left or anything like that. It's just stationary. So that acceleration is gone. Now we need to identify g. And if we go back to the diagram, we notice g was given on the diagram downwards. And so we need to establish a coordinate system so we can write that vector g in terms of our coordinate system. So as is our usual practice, I'm going to just simply define z as being up. And what that allows me to do down here is say that g is equal to minus gk. So this g is just the magnitude, doesn't have any arrow over top of it, and the direction of this g is minus k. So we got rid of the acceleration and we've identified what g is. Of course, these densities will be different in each manometer fluid. So the next thing we need to do is recognize that this equation has 3 components on the left-hand side, but on the right-hand side, the only component that's non-zero is k. So we can just simply extract the z component, and we get that. Okay, so notice here it's a vector equation. There are 3 components, but to get to this, I've just extracted only the z component. So notice there's no vectors on either side of this anymore. So that's the relationship between the pressure gradient, the density, and the acceleration due to gravity. So what this allows us to do is just rearrange this and then integrate both sides. And I'm going to integrate between some 2 points, and I'm going to call them alpha and beta. I want to use a numbering scheme here that I haven't used in my diagram because I'm not talking about any particular points yet. So the next thing we can do to the right-hand side of this equation is assume that rho and g are constant. So we get over here p beta minus p alpha is equal to minus rho g integral from alpha to beta of dz. So this equals minus rho g z beta minus z alpha. P beta minus p alpha. So notice this alpha and beta subscripts can be any 2 points as long as they're in the same fluid, because I assume density is constant here. So we need to go back to our assumptions list because of what we did going from this step to this step. There we assumed rho and g are constants. So rho constant for each fluid and g is constant. Now what we have is we have a working equation. We can write each of these 3 pressure differences now in terms of a density and an elevation difference. So that's what we'll do. We go back to P1 minus P2 now, and we use this equation 3 times. So first thing we get is minus the density of water times G times Z1 minus ZA minus the density of mercury times G ZA minus ZB minus the density of water again times G times ZB minus Z2. So that's just the same equation written 3 times. Notice a very important part of this is that the order of these subscripts 1A, AB, B2 is just reproduced exactly down here. 1A, AB, B2. And this equation is substituted in here exactly like it looks, so this negative comes along for the ride as well. So just be careful and substitute things in carefully, and you'll be fine. So what we'll do now is factor out minus rho w times g from each of these terms. So out front here we have minus rho w times g. So this term, we just have Z1 minus ZA left. This term will have plus the specific gravity of Mercury times ZA minus ZB. Notice it's positive now because we factored out the negative sign here. The G is factored out. This becomes the specific gravity of Mercury. Remember what specific gravity is. It's the density of Mercury divided by the density of water. So when we factor out density of water, we get the specific gravity of Mercury here. And then the last term, again, positive ZB minus Z2. Now we have to worry about these elevation changes. Notice we know the density of water, we know G, we know the specific gravity of Mercury. So there's just these elevation changes to worry about. So let's go back up to our diagram and look at Z1 minus ZA first. Well, we go to the diagram and we notice Z1 minus ZA, we don't know what that is. There's no way to figure out from the information given on this diagram what Z1 minus ZA is. ZB minus ZA is 20. That's labeled here. The other problem is Z2 minus ZB. We don't know what that is either. Z2 minus Z1 is 1 meter. So the only two things we know here are Z2 minus Z1 is 1 meter and ZB minus ZA is 20 centimeters. So we have to go back down to our expression and see how we can take care of this problem. If we go back to this, take a look at what we have right now. Z1 minus ZA and ZB minus Z2. Well, we can rearrange those and call it Z1 minus Z2 plus ZB minus ZA. That's the same thing. And then we still, of course, need our mercury term here. Specific gravity of H2O times ZA minus ZB. Z1 minus Z2, we know. So Z1 minus Z2 will be negative 1 meter. And ZB minus ZA is going to be 20 centimeters. So now we're ready to substitute numbers into these. So I'm just going to write these elevation changes down explicitly here. So Z1 minus Z2 is equal to negative 1 meter. ZB minus ZA is equal to 20 centimeters, or 0.2 meters. And of course, ZA minus ZB that we'll need here is just going to be negative 0.2 meters. So we're ready to substitute numbers in here. The density of water, we were told, was 1,000. And that's kilograms per meter cubed. G is 9.81 meters per second squared. So now we're into the parentheses. Z1 minus Z2 is negative 1. We'll put these all in meters. Plus ZB minus ZA is 0.2. Plus the specific gravity of the mercury, which doesn't have any units, but it was given as 13.56, times ZA minus ZB, which is negative 0.2. And all of those elevation changes are in meters. So we calculate this out and we get our P1 minus P2, and it works out to 34,500 pascals, or 34.5 kilopascals.